Hello everyone, welcome to Tan45Engineering. We are here with yet another video in our mastering data structures and algorithms in Java. Today's topic is time complexity. So let's start. Okay, before going into time complexity, please understand it is one of the most important fundamental concept when it comes to data structures and algorithms. Time complexity is really important when you have to finalize the algorithms. Okay, so what is time complexity? Time complexity measures the amount of time for an algorithm that it will take to complete a function, right? It helps us predict the efficiency of an algorithm. So using time complexity, you can be sure whether one algorithm is more efficient than the other algorithm. So it is very common in interviews, you get asked a question and you have done it and they ask you what is the time complexity. Then you tell them a time complexity and they are like, can you improve upon the time complexity? So for improving upon the time complexity, you will get new logics, but you have to understand time complexity. In earlier video, we have already seen asymptotic notations and why we use omega, why we use big O other than omega and theta. Please check out the past asymptotic notation video as well. So why is time complexity important? Again, it gives us a way to compare two algorithms based on performance. Also helps us in selecting the more efficient algorithms when we are trying to solve for a problem. Plus, if you are solving a small or simpler problem, time complexity may not play a very significant role. But when the data set increases, as it happens in cases for almost all the companies, your scenarios become more valid where you need to choose a better performing algorithm, and in such scenarios you have to calculate the time complexity. You have to understand the time complexity. Okay, so there are different types of time complexity. I'm sure if you have reached out to this video, you are aware there are different set of time complexity that we usually take into account, right? So we'll go through them one by one. So first is constant time. So please pay attention. For the constant time, we denote it as O of 1 because the time is going to remain constant. It does not mean that the total amount of time taken will be constant, but it will not be dependent upon the input, right? So runtime does not depend on the input size. Accessing an element in an array by index. You can see in this piece of code, we have a method get element and we have to return array at the provided index. Let's say the index value provided is 0, so we have to return the 0th element, right? So I'll just quickly show this like this. Let's say we had an array 1 2 3 4 and you are asked to return array of 0. You know this is the value, right? If it was let's say array of 2, you know this is the value. So it does not take you much time. You don't have to traverse the algorithm anything. You simply directly return this value. So the time taken will be constant. It's not dependent upon the length of the array. So it could have, let's say, maybe not ending at 4, 5 6 7 8. But this answer, for this answer again, it will directly return 3. It does not have to go through the complete array. So the time would be constant for this one, right? Okay, so this is simplest time complexity O of 1. Let's move to next. Next we have logarithmic time complexity, log of n. So it increases logarithmically as the input size increases. So this is very common wherever we have to solve for divide and conquer problems, like part of merge sort or this binary search. Binary search is a great example for logarithmic time complexity. So why log of n? Because for each input, your overall time complexity will increase logarithmically. So let's say for when we are doing binary search, right? Let's say for binary search there are only 5 elements, 1 2 3 4 5. So you try to calculate and we have to find the key that is 4, right? So you first look at the middle. It is not there. The key is bigger than the middle point. So now you search in this half. There is no midpoint, so you get this 4. So you return 4. You do not check for 1 2 or 5. But in for 1 2 3 4 5 elements we took two attempts. For 6 also we would have taken 3. For 6 we would have taken 3 attempts. Similarly, if 1 2 3 is only there, right, and the key is 1 or 3, let's say key is 1, First you will check the middle, it's lower, you'll come to this side and you'll find the key. So it is taking less time. Now let's say if the input increases 1 2 3 4 5 6 7 8 9 and you still have to calculate, let's say 1. First you will check in the middle, you come somewhere at 5. Let me make it 10 so that you come at 5. Again it's in the lower half, so you calculate again the middle 3, again the lower half, you come to 2 and then 1, right? So you did not cover all the elements, but you went logarithmically. And there actually when we say log of n, that is O of log n, the base here is actually 2. There are several reasons for keeping 2 as the base, because in computer science we calculate in binaries are 2, it makes more sense. Even if you calculate in other terms, log of let's say base 10, it would not make much difference, since the logarithmic conversion for 2 and 10 or any other value is a constant time, right? That's why we never write the base when we write the time complexity in logs. Okay, so for logarithmic time complexity, you can understand for binary search we have to go through the complete array, but we are not going to search for each element, right? We are going to divide them into half, then divide them into half, then divide them into half, right? So this way we are increasing the value logarithmically. So for the input size 3 we are doing 2 computation. For the input size greater, the computations will increase, but in logarithmic manner. So for let's say input size 8, I think it will be 3 or 4 computations. Okay, now the next one is linear time. That is also a very simple time complexity. The runtime increases linearly with the input size. It's O of n. So you can imagine if the number of elements in the array would increase, the time complexity would increase. Let's say for linear search, we have to return a key when we will find. Okay, we are going to perform a linear search. We are running a for loop, int I equal to 0, I less than array of length I plus plus. We'll try to find the key. Now finding this key could be a constant time thing, so we don't take this into account. But how many times do we have to run this? We have to run this as long as we find the key, and that depends upon how long the array is, right? So a length of array can be assumed n, and our time will increase based on the input or the size of the array. So the time increases with the input. It's a linear time complexity, O of n. Okay, let's go to the next one. Then we have linear arithmetic time complexity. We already understand what is log of n. That by log of n you can always assume it's a divide and conquer, right? Whether it's binary search, whether it's merge sort, quick sort, it's a divide and conquer. Now why the n log n? Because let's say for this example, if we consider this example, when we are performing merge sort, we are dividing them into 2 parts and then dividing the array further into further parts, right? So all the complete array, let's go here. Let's say this was your complete array in the beginning. This was your complete array in the beginning. Oh, come on. Okay. Why is it? Yeah. This is your complete array in the beginning. So first step, you divide this into 2 parts. And then again into 2 parts. Right? And you do the same for this one, and similarly you go down this path as well. This is same as doing the binary search, and this is where we get our log of n. But once for merge sort, you have sorted them. You have sorted the array. They were let's say numbered in different manners. 3 1 2 6 5 9 9 3 4. Okay, at the end when the last 2 elements are left, and the last 2 elements, let's say for example, are 3 and 4, or let's say the last 2 elements are 4 and 3, you know 3 is smaller, it should come on this side, you swap them, so it becomes 3 4. In another array we have, let's say 1 5 7. Now we need to merge them, right? After we have sorted them, we have done the divide, we conquered, we sorted them, we have to merge them back to form our original complete array with the sorted elements. So when we are merging them again, we have to go through all the elements, right? It depends upon how many elements are there on each side. So if the original length of array was small, it was only, let's say, 4 elements, this will get done faster. It was 16 elements, it will take a lot of time, right? So the length of the array will depend as well. So final time complexity would be n log n, right? I hope it is clear. Let's go to next one. Oh, and this one is called linear time complexity, linear plus logarithmic, right? Some of the examples are merge sort, quick sort. And next is quadratic time complexity, O of n square, bubble sort, selection sort. Actually, it's a part of many sorting algorithms. So runtime grows quadratically with the input size. It is very simple to assume directly. You have two for loops, right? Let's so first for loop will run for all the values starting from first till n, and the next loop will run again starting from 1 till n minus 1 or n minus I, or from 0 to n minus I, right? But for each first loop, the second loop is going to run as well. That's why for this loop it is linear. We are going to traverse the complete array once it is O of n. But then we are going for each value inside that loop, we are going for another O of n. So it becomes n square. So let's understand this in a simple manner, okay? I think I can. Okay. Now, let's say we have a for loop. Okay, we have an array 1 2 3 6 7 9 10. Okay, so we want to traverse this array, so we do a for loop. We run from 0 to n. We are going to traverse it completely. Okay, so if this is the case, the time complexity will always come out to be O of n. But now we want to sort it, right? So for each first value, we'll compare it with 1 to 2, then 1 to 3, then 3 to 6, then 6 to 7, 1 to 2, 1 is small. Let's say this was 11. 11 to 2, since 11 is bigger than 2, we'll swap them. So it will become 2 11. Then 11 to 3, we'll swap them. It will become 2 3 11. Right? At the end of first loop, 11 will come in the end. But the rest of the elements are still unsorted. Right? So we need another loop. Okay, 0 to again n minus I. You can run it n minus I or n, does not matter. The important part is that it depends on the length n, right? So now you are running a loop inside a loop. So for each n, each value inside n, let's say n is equal to 4. So we'll say 1 2 3 4. You are going to run this loop 4 times. So for each one, you are going to run this 2 3 4. 2 3 4 2 3 4 2 3 4, or even if you run 1 minus, let's say you run 2 3 for this one, 2 3, or just 2 3 and 4. Okay, anyway, so a loop inside a loop, you get O of n square. And just for understanding, if you have a for loop and it is running through length of n, even if it is n by 2, that means it is dependent upon n, right? Inside the for loop you have another for loop, and inside the other for loop you have another for loop, and all of them are running based on the length or the length of the array, that is n. They could be running for the complete n, they could be running for n by 2, they could be running for n by 3, but they are dependent upon n, right? And it's a loop inside a loop inside a loop. It will become O of n cube, right? I hope it helps. It is the easiest way to calculate the time complexity once you understand that you have to focus only on the major parts, and the major part always would be n where n represents number of elements. Okay, so this is quadratic time complexity. Let's move to next one. Next is exponential time complexity. So this is 2 raised to power n. The runtime doubles with each additional element. It's a really good example for Fibonacci series. You can see if n is 2, we are going to run it for n minus 1, that is Fibonacci of 1, and n minus 2, that is Fibonacci of 0, right? But if the n is 10, we are going to run it for 9 and 8, and then inside 9 we are going to run it for 8 and 7, inside 8 we are going to run it for 7 and 6, inside 7 we are let's go here. So for Fibonacci we can say it is f of n, right? F of n. If the value of n is equal to 2, so it is going to run for f of n minus 1 plus f of n minus 2. So it is going to run for f of 1 and f of 0, right? And we'll get the value. But if the value of n increases, let's say n is equal to 10, now we'll start with f of 9 plus f of 8. For 9 we'll do f of 8 plus f of 7. For 8 we will do f of 7 plus f of 6. You see, and then again for 8 we will do 7 and 6. For 7 we will do 6 and 5. For this 7 we will do 6 and 5. For this 6 we will do 5 and 4. Right? With each number we are increasing it twice. Right? For each value of n we have to do it twice inside it. So we'll go with 2 raised to the power n, because when there were only 2 elements, 2 raised to power 2 is equal to 4. At the max we have 4 computations. But now if value of n is equal to 10, it will take 2 raised to power 10, and it will be a very inefficient algorithm. It will be a very high time complexity. I wouldn't say inefficient algorithm, I would say it will be a really high time complexity, right? So in this case also the output, the algorithm depends on n, right? But how does it depends upon n? That is the time complexity. So it depends with the ratio 2 raised to power n. It's exponential time complexity. Very common for recursive algorithms for finding subset problem, brute force attacks, and brute force problems, and like a Fibonacci sequence. Okay, the last the second one is factorial time complexity, O of n. I forgot what the symbol is called. N factorial. Yeah, n factorial. Okay, the runtime grows factorially with input size. So brute force algorithm uses n factorial to explore all the permutations. When we have to explore all the possibilities, we go and check all the possible paths. It's like when you have to find a path in a maze, you'll search with all the possible paths. So the time complexity is going to be in terms of factorial. In this case also, if we see, we have to generate permutations, right? We'll generate the permutations, but we call this generate permutation method again with an increased index, right? So what will happen, that the overall solution of this algorithm, when we say f of n factorial, we mean it depends on f of n plus f of n minus 1 plus f of n minus 2 plus f of this way until n reaches 0, right? So this depends upon n, and then inside each n we have to calculate all the path. For each n we have to calculate next set of path and then next set of path. So the time complexity is going to be f of n factorial. So for one easier example to understand, right? When we were talking about merge sort, we get this final time complexity of n log n, because for each value of n we have the time complexity of log of n. What happens in factorial cases, for each value of n we have a then time complexity of n minus 1 factorial. Then for each value of n minus 1 factorial we have a time we have to run this again by n minus 2 factorial. So we call the time complexity as O of n factorial. Okay. The example is of course generating all permutations, solving a maze or brute force. Let's move next. So these are the most frequently used time complexities examples. So we'll just take a quick look again. Constant time, O of 1, very easy. Logarithmic time, log n. Whenever you have a binary search or you have a divide and conquer, whenever it is to be divided by 2, you can understand it's a log n time complexity. But if you have to do log n again and again, I'll come to it. If you have to perform log n again and again for a n amount of time, you can go with n log n. Okay. For O of n, it's simple. It's clearly depends upon number of input. If the number of input is 4, we are going to take 4 units of time complexity. Okay. Then we have linear rhythmic time complexity. So now log of n again depends upon n, because for these two merge sort we use log n, but for this merge we use n again, right? So it will be n log n. Also, okay, I'll come to it. Quadratic time complexity, n raised to the power 2. It goes quadratically with the input size. Exponential time complexity, 2 raised to power n, runtime doubles with each additional element, right? Factorial time complexity and factorial we just discussed. Now, so how to analyze time complexity? Okay, that is important part. We have to focus on the most significant terms when determining time complexity, and we have to remove all the less significant terms. We always ignore the constants or the constant coefficients, because they does not alter the growth rate of an algorithm that much. Okay, let's quickly understand with a quick example. Give me 1 second. Okay, let's say we have a for loop. Okay, let's say we have a for loop. We don't know what we are going to do. We only have a for loop. Okay, it is running for from 0 to n. We already know in the time complexity section that we got our O of n. Okay, inside this, let's remove it here. Okay, inside this we are doing some calculations. Okay, I'm calculating the sum, and I'm doing some calculations here. Calculate, let's say I'm calling another method for calculation. Okay, but this method will be called for each value of n, right? It's not like it will not be called for other values of n, it will be called for each values of n. So this method's time complexity becomes constant for this overall time complexity. So we can take this complexity as c, constant. So we write it, instead of O of n, it becomes O of n into c. Now O of n into c is still dependent upon n only, right? So we can simply call it O of n. Okay, now inside this for loop, we now encounter that there is another for loop. Okay, now you have to understand this for loop is again running from 0 to n. So the value of n is important for this one. So this time complexity is important, right? So it will become again O of n into n. We are at O of n square. Now once this for loop ends, there is another for loop. Again 0 to n it is running. It is also doing some calculations in constant time. It is also doing some calculations in constant time. We could take constant calculation as c1, c2, c3. It wouldn't matter, since they are constant time, we are going to ignore them anyway. But for this for loop, when we encounter a for loop inside a for loop, we increase the time complexity of O of n square. But there is another for loop. It is inside the first for loop but outside the second for loop. So first for loop, second for loop, and third for loop. So now how will we calculate the time complexity? If there are two for loops, forget the outside for loop. Okay, now the time complexity will look, or let's remember the outside for loop. Okay, time complexity from this one will come as O of n, and for this one it will be multiplied by n, as we saw up till here, n square. But now we have another n loop, so it should be O of n, that is for outer for loop, and inside it is n plus n, right? It is not multiplied, because once this is over then we start this, so it's not multiplying, rather addition. So it will be O of n multiplied by n plus n. So this will become O of n into 2n. So it will become, now 2n is again dependent upon just n alone, right? We have to calculate the time complexity, not the time, right? So 2n is same as n. So because if it is dependent upon 2n, that means it is dependent upon n, because 2 is constant. So we can say time complexity is again O of n into n, and it is O of n square. Okay, Though we can see three loops, but these loops are not inside each other. Third loop is not inside second loop. So we focus on the major parts like this one, this one, this one. We remove the constants. We don't care about the constants. It's a constant time taken, and we can give out the final time complexity of a algorithm. Hope that helps. Okay, now in the conclusion, understanding time complexity is really crucial, not only for interviews but for actually writing very efficient codes. When you are working on really big projects, the time complexity of the algorithms that you use will matter a lot. It can make a difference of time between minutes and days. Okay, so by recognizing and understanding the algorithms by their time complexity, you can make informed decision on which algorithms are suitable for different scenarios. That again we'll be learning when we'll be learning different algorithms. We'll get to choose why we choose certain algorithms for sorting above other algorithms that takes more time complexity. Okay. So that's all from today's video, everyone. If you have anything, please let me know in the comment section. It's a really important video for all the algorithms in this for all the videos in this series. So please understand time complexity very well. If you have any doubt, please let me know in the comments. I'll be more than happy to respond to them. Okay. In the end, thank you, everyone. Please like, share, and subscribe.